Jai Hind everyone. Today we are going to start with mining data stream. So first of all, we need to understand what does it mean by streaming data. As the name is indicating, streaming data, that is the data which is generated in continuation manner, right? That is continuously generated, especially in very high volumes and with a very high velocity as well, right? At a very high speed, we can say. Fine. A streaming data sources would typically consist of a stream of logs that record events as they happen, like excuse me, as a user clicking on a link on a web page or a sensor reporting the current temperature, right? That means the data which is getting generated in a continuation manner, that is the streaming data, right? Here we have few of the common examples of streaming data, which includes IoT sensors, server and the security logs, real-time advertising, clickstream data from various applications and the various websites. Now we see what are the challenges of streaming data. Data arrives in a stream or streams, and if it is not processed immediately or stored, then it is lost forever, right? What we are saying, ki data is arriving in few of the streams, or we can say a particular stream, and it becomes very difficult to store the real-time data immediately, right? But if we are not able to store the data immediately, then it can be lost forever, right? So moreover, we shall assume that the data arrives so rapidly that it is not feasible to store it at all in real-time environment, in the active storage, right? That means if we are using a conventional database, then it is not possible for us, right? And then interact with it at the time we choose, right? So it becomes very big challenge in the case of streaming data. A stream is defined as a possibly unbounded sequence of data items or records that may or may not be related to or correlated with each other, right? Each data is generally time-stamped, and sometimes in some of the cases, in some of the applications where the location is being traced, is being geotagged, right? We can see in many of the cases, the data is generally time-stamped, at what time the data, the transaction was started, at which time the event has happened, and so on and so forth, right? So we say the data is generally time-stamped, and if it is required, it will be geotagged. Now, before going further, we'll start. There is a difference in the traditional data processing versus stream processing. So what is the difference? Here we see a batch processing, where a batch is a collection of data points that have been grouped together within a specific time interval. Another term often used for this is a window of data, right? We can use that. Streaming processing deals with continuous data and is key to turning big data into the fast data, right? Under the batch processing model, a set of data is collected over a period of time and then fed into an analytics system. In the other words, you collect a batch of information, then send the entire batch in a one go for processing. For example, our credit card bill generation, our telephone postpaid bill generation, electricity bill generation, and so on and so forth. They collect the information for the entire month, and at the end of the month, the bill is getting generated, right? So it is a kind of a batch processing model, right? Under the streaming model, data is fed into analytics tools piece by piece. The processing is usually done in real time. It is not like they are storing the information, they are storing the data, and at the end of the month or at the end of the day that will be processed and so on. The data is getting processed in a real time. That is the main difference in the batch processing system and the streaming data, right? Data streaming. So here we are having some of the use cases for the batch processing and some of the use cases for stream processing. In the case of batch processing, the most popular use cases are payroll, billing, and orders from the customers, right? And the use cases for the stream processing includes fraud detection. We cannot wait that let 5 fraud be happen and then we'll detect the frauds. We cannot wait for that, right? We cannot collect a batch for the frauds. We cannot afford to have a further fraud, right? Social media sentiment analysis, log monitoring, analyzing customer behavior, and so on. That means wherever we are working on a real-time data, we are working on data streaming. A batch is a collection of data points that have been grouped together within a specific time interval, as we have discussed in the previous slide. Another term often used for this is a window of data, right? That's what we have discussed. Fine. So, what we can say, streaming processing deals with continuous data and is a key to turning big data into the fast data, right? In a nutshell, we can see that these are the differences, these are the major differences in between batch processing and stream processing, right? So, now the question arises, what is the streaming data? Here we see input data. Input data that is there in many of the formats. Fine. Then there is a stream processing engine which is processing the streams on a real-time basis, and here we have some of the analytics algorithms working on over here, and then we are getting the output. The output streams are there, right? So that is how the data streaming is getting done. Manage a small time window, unbounded data, data not correlated, data can only be time-stamped or geotagged, through which we are able to analyze the data at which particular time, what was the recorded temperature, what is the reading of a particular sensor, and so on. So, how this stream model works? Streams may be archived in a large archival store, but we assume it is not possible to answer the queries from the archival store in a real-time environment, right? It could be examined only under some of the circumstances, special circumstances, using multiple time-consuming retrieval processes. There is also a working store into which summaries, or we can say the parts of the streams, may be kept, may be placed, and which can be used to answer the queries, right? The working store might be disk, it might be our main memory. It depends on the application where we need, how fast we need to process the query. But either way, it is of sufficiently limited capacity that cannot store all the data from all the streams. It is always a big challenge for us, for the developers, for the data scientists, you can say, to manage the storage, right? When we are working on a real-time data and a huge amount of data, a large amount of data at a high speed, we are collecting, we are getting. So, it is always a big challenge to manage that data, right? So, in many of the data mining situations, we do not know the entire data set in advance. Stream management is very important when the input rate is controlled externally, like Google queries, like Twitter or Facebook status update. We can see within a fraction of milliseconds, not even a seconds, how many Google queries are getting generated, how many Twitters or Facebook statuses are getting updated. we can think of the data as infinite and non-stationary, that is, the distribution changes over a time. So, what are the problems on the data streams? The type of queries one wants or answer on a data stream is, number one, how to sample data from a stream. Sampling is a main, like you can say, a question, a problem. How to sample from a stream where we can not be sure that whatever data is coming to us at the same rate, in the same format, the next we will be having the other data as well. Construct a random sample. Queries over sliding window. Number of items of type X in the last k elements of the stream. Filtering a data stream. Select elements with the property X, for example, from the stream. With X property we are working. Next time maybe we need to work with another property. Counting distinct elements. Number of distinct elements in the last k elements of the stream. Suppose Amazon wants to check that in the past 5 hours or in the past 10 hours, how many different customers has done a login onto my application. Estimating movements, finding frequent elements, and so on and so forth. So, now we will be discussing a DSMS, that is a data stream management system, right? How the data streaming is getting managed. We can view a stream processor as a kind of a data management system. As we all are aware, with a traditional system, any number of streams can enter the system. Each stream can provide elements at its own schedule. They need not have the same data rates or the same data types, and the time between the elements of one stream need not be uniform. The fact that the rate of arrival of stream elements is not under the control of the system distinguishes stream processing from the processing of data that goes on within a database management system. Graphically, we can represent the DSMS like this. We see streams entering the input data. We can see the streams are coming into multiple formats. It could be in a numeric format, say few of the letters are there, in a binary format, and so on and so forth. Then we are having some standing queries are there. There is a stream processor who is processing all these things. We are having a limited working storage. A storage is there. Archival storage is there, for which we have talked about that it is very difficult to work on an archival storage while streaming data. Somehow we can retrieve the data with the help of complex queries, and which is a time consuming process, right? After processing, then we will be having some output stream. Few of the examples of stream sources we have. Number one, sensor data. Sensor data to learn something about ocean behavior, we can say. We might want to deploy 1,000,000 sensors, each sending back a stream at a rate of 10 per second, right? 1,000,000 sensor is not very many. There would be one for every 150 square miles of ocean. Now, we have 3.5 TBs or terabytes arriving every day. Now, we can think what amount of data is getting generated and we need to be handled. And we definitely need to think about what can be kept in working storage and what can only be archived, right? So, that is a sensor data. Second, we have image data. Here, for example, satellites often send down to Earth streams consisting of many terabytes of images per day. Surveillance cameras produces images with the lower resolution than the satellites, but there can be many of them, each producing a stream of image at intervals like, say, 1 second, right? London is said to have 6 million such cameras, each producing a stream, right? Next example, we can consider internet and the web traffic. A switching node in the middle of the internet receives streams of IP packets from many inputs and routes them to its output. Normally, the job of the switch is to transmit the data and not to retain it or to query it. But here, there is a tendency to put more capability into the switches for like the ability to detect DOS attack, that is denial of service attack, or the ability to reroute the packet based on information about congestion in the network. Fine. Websites receive streams of various types. For example, Google receives several 100 million search queries per day. Fine. Yahoo accepts billions of clicks per day on its various sites. Many interesting things can be learned from these streams. Fine. For example, an increase in the queries like sore throat enables us to track the spread of viruses. This is the most popular example, as we have seen recently. We have gone through the pandemic era, right? And there we have seen there was a sudden spike in the query of a sore throat, right? A sudden increase in the click rate for a link could indicate some news connected to that page, right? Or it could mean that the link is broken and needs to be repaired. But yes, if there is a sudden increase in few of the parameters, few of the queries, then it could be an alarming situation as well. For example, a COVID situation, right? So we'll see what are the stream queries. Websites often like to report the number of unique users over the past month. If we think of each login as a stream element, we can maintain a window that is all logins in the most recent month. We must associate the arrival time with each login so we know when it no longer belongs to that particular window, right? If we think of the window as a relation login, then it is simple to get the number of unique users over the past month. For that, there will be a simple SQL query like select count distinct name from the logins where time is greater than t. Now the question arises, what does it mean by this t? What this t is doing over here? T is a constant that represents the time 1 month before the current time, right? So that is how the stream queries are working. Now, how do we manage streaming data? For managing the streaming data, we are having multiple algorithms. Number 1, sampling. Number 2, filtering. For that, the famous algorithm is Bloom's filtering. Third one, count distinct problem. The count distinct problem, the famous algorithm where here is the FM algorithm, that is Flageolet-Martin algorithm, which I am going to discuss in this particular lecture. Estimating movements and then counting ones in a window and decaying windows. Out of all of these algorithms, in this particular lecture, I am going to discuss this FM algorithm, right? So, first of all, we'll see what is the algorithm. Then we will be discussing one example, right? Count distinct problem and FM Martin algorithm is the algorithm which falls into that particular category. So, the steps are apply a hash function on the input stream, whatever input stream that is being given to us, we have to apply a hash function on that. Then convert the result into its binary equivalent, right? Then we have to count the number of trailing zeros in the binary equivalent. What is the trailing zeros, say 0, 1, 0, 0. This is a binary equivalent. Then the trailing number of trailing zeros is 2, right? Fine. Maximum number of trailing zero is R. They need to find out what is the maximum number of trailing zero, right? And then at the last step, we need to find out R. R is equal to 2 to the power R. That is the number of distinct element. So now we will be discussing one of the example. It will be more clearer. Determine the distinct elements where the input stream x is equal to 1, 3, 2, 1, 2, 3, 4, 3, 1, 2, 3, 1, right? And the hash function is given to us, that is hx equals to 6x plus 1 mod 5. Now, as we can see in the algorithm, the first step was calculate hash function. We need to put the value of stream one by one in the given hash function. So, first integer in the given stream is 1. 6 multiplied by 1 plus 1 mod 5 that is equal to 6 into 1, that is 1, 6 plus 1, 6 into 1, that is 6 plus 1 mod 5, that means 7 mod 5 is equal to 2. Similarly, we find for the next integer in the stream, that is 3, h3, 6 into 3 plus 1 mod 5, we'll see the value, it will be 4. Next is h2, 6 into 2 plus 1 mod 5, we'll find out the value is 3. Again h1, we know the value is equal to, that is 2. Then the next integer in the stream, that is h2, we have already calculated, is equal to 3. h3, yes, we know, that is 4. h4 is h4, okay, h4 we need to calculate. That is 6 into 4 plus 1 mod 5 it becomes 0, okay, then H3 again, that is 4, H1, two, H2, 3, H3, that is 4, and the last integer in the stream is H1, that is 2, right? So that's how we have calculated all the hash functions. Now, according to the algorithm, the second step says we need to write the binary equivalent of all the calculated values. So, the binary equivalent for 2 is 0, 1, 0. Binary equivalent for 3. The next is 4. The binary equivalent of 4, that is 1, 0, 0. For 3, it is 0, 1, 1. For 2, it is 0, 1, 0. Then again 0, 1, 1, 1, 0, 0. For the 0, it is obviously 0, 0, 0. Then again 1, 0, 0. For 2, it is 0, 1, 0, 0, 1, 1, 1, 0, 0. Then 0, 1, 0. Right? Step number 2. We need to find out the binary equivalent for the hash function calculated. Now, according to the algorithm, what is the third step? The third step says find out the trailing zeros. Right? We need to find out the trailing zeros. How many trailing zeros are there? Yes, that is only 1. Here we see that is 2. Here 0. Here we have 1. Again 0. Here we have 2. There is 0 because it is all zeros. Trailing 0 says at least there should be one changing bit. Fine. There is no any changing bit. No one is there. All the zeros are there. So, there is no trailing 0, right? So, 1, 0, 0. Trailing zeros are 2. Here, trailing 0 is 1, 0, 2 and 1. Right. Now, according to the algorithm, what is the fourth step? Write the value of the maximum number of trailing 0. Maximum number of trailing 0. So, what is the maximum number of trailing 0? That is 2. Yes, we can easily see from there. Fine. So, we need to find out R. R is equal to 2 raised to the power small r. This is what? Small r. This is the value of small r, right? And R raised to the power small r, that equals to 2 raised to the power 2. That means 4 distinct elements are there in the given stream, in the given input stream. Fine. So, that's what we were calculating. We were trying to find out that how many distinct elements are there in this algorithm, in this given stream, right? Okay, here these are the references from where I have included the contents in my slides. Thank you.